In new barns, Farmer John is creating a series of barns connected by bidirectional pathways. He's going to give Q queries, either telling us to build a new barn connected to the barn he gives, or give the longest possible distance that the current barn he queries has to any other barn. We want to get the output for all of these queries that he gives us. Let's go look at the algorithm for this question. Since we know that there are bidirectional edges in between the different barns, we can treat this as a graph question. So nodes are going to be barns, and then the bidirectional edges are just going to be our edges. And when we look at the way that this question is querying, we can basically ask ourselves, how do we know the longest possible path quickly from any node to a certain node? Well, let's say we put and create an intermediate node. So let's say we're going to be querying the purple node, and in order to reach it, let's say we have to go through this root node here. Well, the longest possible path is just going to be the depth of the purple node, in this case 1, and then the longest possible depth of any other node from the root node. And so what this ends up doing is, if we assign lots of different nodes as our root node, we can basically find our path consistently as the distance of the depth from the root to the current node, and plus the distance from the root to any other node in a different subtree, so the longest possible depth. In order to find the best possible nodes to be our root node, we're going to use the centroid decomposition algorithm. So centroid decomposition is basically where we're going to find any node, and then as long as this node is able to split its subtrees so that each one of these subtrees has a size of less than half the entire tree, then it's going to be a possible centroid. And in each tree, there's only going to be one centroid, and so in order to find multiple different roots to start at, we're going to use centroid decomposition, so breaking down a tree from here, and then finding the centroid from here, and finding the centroid from here, all the way down until we reach the individual nodes. Basically, we're going to be using centroid decomposition. And so, this is all assuming, by the way, that we don't address the active and inactive problem of this question. So, in the case that every barn we have does not need to activate, so we just assume they're all already active, we would just read in the input, and then for the input, we would just have these individual trees. For each one, we're going to do centroid decomposition, and then for every node we query, we're going to go up, and then for every centroid along the way, perhaps this one, and then maybe this one, we're going to find the maximum possible answer there. So that's just going to, again, be the maximum possible distance from this node, plus the depth from this node to our current node. Since we have to activate the individual nodes, we're going to go down, and then we're going to first do centroid decomposition on our tree. And then for every tree, we're going to store in our tree data structure the tallest and the second tallest different depths. And the reason we're going to store 2 is because let's say the node we're querying is on the path for the deepest possible answer. Well, in that case, we would return back the answer of this height, so this is the deepest possible node, plus the distance or the depth of the node we're querying. So let's say it's this node. So we would inaccurately say the answer is this 1 plus this 3, because the actual shortest distance between this node and this node is 2. So basically, if they're on the same subtree, it would record back the wrong answer. So we're going to store the highest and also the second highest, because if the node we're querying is on the path for the highest, we can just get the depth of the second highest instead. In addition to that, the individual nodes are going to store a list of all of their ancestors. So for this specific node, it's going to go up through the list, and for each one of its centroid ancestors, it's going to store the depth from it to that node. And so what's going to happen is, once we activate a node, we're basically going to go up through its centroid ancestors, and for each one of these trees, we're going to update its maximum 2 heights with this node's height. So basically, if this depth happens to be the new longest or the second longest depth, then for each one of its ancestors, we're going to update their trees with this depth. And that way, as we go through, the 2 numbers for the 2 highest depths for every tree stored are only going to contain the depths of activated nodes, since every time we activate it, we're going to add it in, and the inactivated node depths aren't going to be included in the 2 highest for each node yet. And then so what we're going to do is, after we finish updating, when we query, we're just going to very simply go, and for every node, we're going to go up, and then basically check its answer as the depth plus the highest non-same subtree depth. And then when we update, we're going to take each one, and then we're going to update all of the trees on the path above it. So let's go see how we can code this. We're going to store our program in a couple different structures. We're going to store our tree with its top node, its 2 highest heights, and then the ID of the child that contains the highest height. And we're going to store every node in our structure of node. So that's going to have used and size. Used is going to be used for whenever we actually go through and use the node. We're going to have our edges list for the ADJ or the adjacency list normally. And then we're also going to store the size of the subtree. We're also going to store our ancestor list called T nodes. This is going to be a vector of structures. Each node is going to contain its ID and then the depth of that node. When we read in our input, we can note that we don't know the number of nodes or the number of barns that we have. And so in order to get around this, we're basically going to first read in our input into a vector of pairs. We're going to clarify them and classify them by whether they are a build or a query. And if they're a build, we're just going to add 1 to n. Once that's done, we're going to loop through it again, resize all of our values now that we know the number of nodes, and then the second time we read through, we're going to start by pushing into our edges lists. So if it's a build where we're starting a new tree, we're going to push back the ID into a roots list. Otherwise, we're just going to update the edges list for the other 2 nodes. And then each time, since whenever we put in a new build, we're going to also keep track of our current node ID by literally keeping track of a number and then adding 1 every time we get to a new build node. Once we finish with that, we know we now have a list of all of the roots. So we're just going to loop through, and for each one of these roots, they have their own tree. And for each tree, we're going to go and decompose. So for our actual centroid decomposition, we're going to have a couple functions. First is our decompose function. So this is our pre-setup. And so for this, we're going to take in 2 arguments or parameters, the node and its parent. We're going to find its size, and then find the centroid of this tree, and then we're going to mark it as used, or the centroid as used, and then we're going to create a new tree for this centroid. Its top node is going to be n, and then we're going to go down recursively and update the depth of every node in this tree. Once we've done that, we're then going to go and we're going to loop through and then run recursion for the decompose function. So let's go step by step through this function again. We're going to find the size of its subtree. And for the find size function, we're going to take in the same parameters of the node and its parent. We're going to do a very simple DFS and then recursively go down. We're also going to check here, when we're looping through that this node's children, we're going to check first if the child is the parent, and second, whether or not it's been used. If neither of them is true, then we're just going to add the size of the child subtree to our subtree. And this DFS is going to return the size of this subtree. Once we have the size, we can then run find centroid. Just like with normal centroid decomposition, we're going to have our find centroid function. For this, we're going to loop through the children of this node. For every child that we loop through, we're going to check to see whether or not the size of that subtree is greater than or equal to half of the size of the main tree. And if it is, then we know that our current node can't be the subtree centroid. So we're just going to recursively go in and then assume that this child is going to be the centroid. If we reach a point where all of the children of a node have less than half of the subtree, then we know that this node is going to be the centroid, so we're going to return it as our answer. Now that we have our centroid back in our decompose function, we can go down, update the depths for every node, and for this specifically, we're going to go down, and then for every node, we're going to go down their t-nodes list, and then for the root of this node, or the current n we're on in our decompose function, we're going to update the depth of this in the n nodes t-nodes list. So for our update depth function, we're going to have 4 different parameters: the node, its parent, and then also the root and the current depth. So for every node, we're going to push back the root and its current depth, and then we're going to go down through its children, again doing a DFS, and then for each one, we're going to update the depth of its child and move the depth up 1. Once we've updated the depths of everything, we're going to go down through the children and then continue with our decompose function until we've decomposed and found the centroid of the entire tree. Once that's done, we've effectively created different trees with centroid decomposition for every tree in this problem. So now what we're going to do is we're going to go through the input and do our build and query again. We're going to loop through all of the commands, and then we're going to check to see first whether it's a build or a query. So if it's a build, we're going to take our node, and I'm going to make this program easier by just assigning it to n, and then I'm going to start looping through all of its ancestors, or all of its parents. And so this is a long loop, but we'll go through it step by step. So we're going to loop down through from the highest to the lowest. This is going to be the root, and then we're going to keep going down. As we loop through the ancestor nodes, for each one, we're going to assign tn to the actual node, and then t to its tree. And we're going to update the 2 heights for its tree. First, if the depth is currently greater than the height of the greatest height in this tree, then we're going to be able to assign the greatest height to our current depth. And then there's a small case here where if the previous height or the previous node we had was also the highest height, then we can't assign height 2 to it, since those 2 are effectively part of the same child branch. So as long as the current highest height isn't part of this subtree branch already, then we're just going to go down, and then we're going to assign height 2 to its height, and then effectively shift them down. Otherwise, we're going to check if it's the second highest height, and with the similar conditions, if it's the second highest height, then we're going to just assign height 2 to the current depth. We're also going to keep assigning previous as the top, and so this loop is going to keep running until we've effectively updated every tree with this node. And then over here, we're also going to add one to our current node. So that's pretty much it for build. When we actually go and we query, we're going to go over here, and then we're going to check a couple conditions. So this code here, we're going to go down line by line. Again, we're going to mark our current node as n, and then we're also going to loop down through. And for each one of our ancestors here, we're going to check first to see if this ancestor root is activated. If this node is not activated, then the path here doesn't count as our maximum. So if the path doesn't count as our maximum, we can't really use it in our answer. So we're just going to assign our previous as this current, and then we're just going to continue on. But as long as this current node is activated, then we can try and find the answer. So we're going to check to make sure if the top highest subtree, if the child that had that subtree is part of this current subtree, so we can tell that by whether or not it's previous. If it is, then we need to go to the second highest subtree. So that's why we have this if-else condition. But as long as the first highest subtree is not the same subtree we're in currently, then our answer is the maximum of itself and the current node's depth along with the height. So it's either the first highest subtree or the second highest subtree, depending on whether or not the first highest subtree is the same subtree that our node is in. And then so we're just going to go down through all of these, and by the time we're here, we'll be able to get the answer for the longest possible path. And so that's going to be what we print out for our query. And that's pretty much the end of our program.